Hi everyone, I'm Clement Lavoillotte and I work for Provadis, and I'm going to talk about privilege file manipulation and how it can be abused to perform a privilege escalation on Windows systems. So, as I said, the attack surface of file manipulation on Windows, and turning arbitrary file read or arbitrary file write bugs into privilege escalation with a small focus on file deletion or AV quarantine bugs. And we'll show some actual example of bugs that we found in popular products, as well as some techniques and tools to exploit these bugs. Oh yeah, and that one too. I'll start with the first demo here. So, with the help of our friend McAfee Endpoint Security, we see that we have some log files here, and that on these log files, we have full control granted to the everyone group. And we're in an unprivileged user session. So we run some magic. Go to system32. Trigger an update. And we see here a wild DLL appears. We copy some content. And here is our system shell. So, privileged file manipulation bugs, basically, these are bugs in file operations that are performed by privileged processes, so privileged services, for instance, driver or stuff like that. And of course, when those privileged components manipulate files that are accessible or that the user has some control over this file, well, shit happens. It actually works with different kind of resources. It's a basic principle in privilege escalation, but files are just an easy target and often overlooked one. These examples are well known to pen testers. For instance, if you have an executable that is user writable by any user, but that is used to, for instance, run a service with a system user account, well, you have an obvious path to privilege escalation. And it's actually quite common in software, even in security software, thanks to these, for instance, common mistakes like access rights misconfiguration, accessing user-owned files without impersonation, or, for instance, where there is the user can manipulate the file between the time it is checked and between the time it is used. And because these are logic bugs, they are usually very stable. They don't require memory corruption or other risky stuff. And they often survive code refactoring, so you can find the same bug in different versions of the same product, for instance. And to find these bugs, or at least the easy one, you usually don't need to start a long and tedious process of reverse engineering the product. You can just fire up Procmon, Process Monitor, and look at what the product does, and then, for instance, try to change some stuff in whatever you can access in the product from your unprivileged user account, and see how the product reacts. You will also need a way to display ACLs on files, so you can just use Explorer, as we saw, or use whatever tool you prefer. And to exploit these bugs, we basically want to make the privilege component do something that is useful for us, attacker. So, for instance, if we have an arbitrary file read bug, we can try to read one of these three hives to grab the secrets that are stored inside them, like, for instance, the administrator's password hash. And if we have an arbitrary file write, when the usual way, for instance, is to either replace an existing binary or to drop a DLL in the path and try to hijack another privileged process, for instance, to gain code execution in a privileged process. And there is also a nice trick found by James Forshaw that basically uses the Jackhub service, which runs as system. And this service can be made to load a file with any name and any extension as long as it's in the system32 folder. So if you have an arbitrary file write bug, you can just drop a file in the system32 folder. Even if you don't control the name of the file, you can then load it as a DLL in the Jackhub service. But of course, you will need a way to control the content of the file so that you can put your evil code in there. And we're going to talk a bit about arbitrary file delete a bit later. So these are the main techniques that we can use to abuse this type of bugs. They were published by James Forshaw along with some specific tools to exploit them. We're going to see some of them. And we can also use for some of these techniques, we can also use some built-in tools in Windows, like just plain old PowerShell. And thanks to this technique, many file system attacks that once were mostly difficult to exploit, or even sometimes considered non-exploitable, are now actually quite easy to exploit. So the first technique is the NTFS mount point or junction. It's basically just a redirection of a directory to another directory. And you can create those as a non-privileged user. So for instance here, if a process tries to access the path cdir file.exe, it will actually access cother file.exe. Object manager symbolic links are basically symbolic links in the object manager namespace, because unprivileged user cannot create file system symbolic links. There is a specific privilege for that, but they can create symbolic links in the object manager namespace in an object directory. And opportunistic locks are basically a kind of lock that you can place on a file, again as a non-privileged user. And if an external process tries to access that file, it won't be able to do so before you remove that lock. So it's really handy to exploit, for instance, race conditions, and to make it really easy to and really stable to perform some of these type of attacks. It does have some limitations, like for instance, it does not allow you to granularly allow just one access. It's once you leave the lock, well, basically all access that are waiting will occur. And the most powerful techniques are the combination of these previous techniques. So for instance, if you combine directory junction with an object manager symbolic link, you get something that behaves like a symbolic link, like a file system level symbolic link. So basically, for instance, if you have a path directory cdir, you can redirect it, turn it into a junction to the object directory RPC control. And in that object directory, you can create a symbolic link that points to another file. So you have a functional equivalent of a symbolic link. And if you combine this with an oplock, so you create a symbolic link as before, and place an oplock on the target file, on the target of the symbolic link. And when that file is accessed, you change the symbolic link to point to another file. So this gives you a path. So here, for instance, cdir file.txt that is parsed, that is reparsed as a first path and then on the first access has another path. So subsequent access will go to the other file. And this again is also useful to exploit, for instance, talk2 bugs. The typical example of an arbitrary file write bug is the creation of a log file with too many privileges. So, for instance, many privileged processes will create log files, but on the log that are created, because unprivileged users also need to, for instance, add content to this file, these log files have a very permissive LCL set on them, and the creation of the log file itself does not use impersonation. So this is actually pretty common. It was found several times just this year, for instance, on multiple components. As well as variants, for instance, instead of an arbitrary file write, you have an arbitrary ACL set. So an arbitrary ACL that is set on your file. And this was, for example, used in these two bugs, so one in Windows component and the one in the ALPC bugs that the first speaker talked about. So these two bugs were actually quite more harder to find than just Fiery Procmon. They both have really awesome write-ups that I would encourage you to read, but they also are some DACL set bugs that are much easier to find in, let's say, less mature component than software than Windows. So the bug that you saw on the first demo was basically exploited like this. So first we delete all the log file in the logs folder so that we can change it into a Junction, because you need the folder to be empty to create a Junction. So we redirect it to the RPC control directory and create a symbolic link with the name of a log file that we know will get created or will get accessed by the privileged process, and make that symlink point to the file we actually want to create. So when we trigger the log creation, so in the demo by clicking on update, the DLL is created, and because the program thinks it's the log file, it will set the same ACL as it does for all log files. That is a very permissive one. So we can then use that DLL dropping feature to hijack a privileged process, or just redirect the logs directory to system32, create a log file even if its name ends with .log, and use the DiagHub trick to load it. A word about AV file scanning, because it's really interesting for this type of bug, because files are often accessed with high privileges, for instance, to remove them or stuff like that. But it can be easily triggered by unprivileged users. So it's really a nice target for a privilege escalation. And of course, it has a lot of abuse potential, because these are all operations that your typical AV will perform. But there are as many roads to privilege escalation, potential privilege escalation. Of course, AV has a lot of other attack surface. It's pretty huge, but the reason we choose it for the file bugs is that it's kind of mandatory for an AV to access files, so it's really a prime target for this type of bugs. An example of a bug on file restore is the AVgator type of bugs, which is basically a logic bug found by Florent Bogner this year, I think, that abuses the file restore process. So You create a file with the name and content you want. For instance, evil.dll, and you put it into a quarantine, either manually or by tricking the AV to quarantine it. And before restoring it, you turn its parent directory to a junction that points to the folder you want to create the file into, so that when the restore happens, it will actually create the file in the folder you want to, even if you, as an privileged user, don't have access to write access to that folder. An example of a similar bug that we found last year is in the Symantec endpoint protection, where there was actually an access right check before the file was restored, but there was no impersonation on the actual file write operation, so a kind of a talk-to bug. And the race was really easy to win, because if you wanted to overwrite an existing file, you would get a nice prompt, and the file write would happen only after that prompt, and the check would happen before the prompt. So you just have all the time in the world to change the folder. It was fixed last year by creating a temporary file to prevent changing the parent directory to a junction or stuff like that. And we found some very lead bypass, which is right-click, delete the temporary file, and you can just then proceed as before. So the exploitation looks pretty much like the AV getter or the previous bug we saw, but we can show it here. So for this demo, we'll target the sethc.exe program, which is the program that pops some annoying windows when you press 5-time shift, for instance. So we're still running in an unprivileged user session. And we can see that the hashes are different, for instance, between sethc and cmd.exe. And we are going to create a temporary folder, another one here. And in that folder, we are going to create a file which has the same name as the file we want to overwrite. So sethc.exe. And we put it into quarantine manually, because Symantec lets you do that as an unprivileged user. No reason why. So the file is removed, and we can recreate another one with the same name, so that we get our nice overwrite prompt. And just after clicking that button, we jump to the folder to delete the temporary file and its parent folder, and replace that folder with a junction that points to system32. So here is our system32. With sethc.exe that has not yet been overwritten. And now it's gone. We see that it has a null size. And if we go into the property of the file, we can see that we are the proud owner of sethc.exe. So we can now overwrite the content of that file, for instance, with the content from cmd.exe. And then open the secure desktop and press shift 5 times. It will run sethc.exe. Because we're on the secure desktop, it will run it as system. So another privilege escalation that also abuses the file restore process that was found on multiple products is basically an access right misconfiguration on the quarantine files. So if user can basically modify this file, the privileged product do the restore with full privileges without user impersonation, then you can exploit this. Basically, for instance, you can change directly the content of the file in the quarantine file. Usually there is some kind of XOR or stuff like that, but it's still quite easy to change. And you can also change eventually the metadata. So for instance, sometimes in the metadata you have like the restore path, so you can directly choose the path and you don't have to create another junction. Or for instance, registry keys that will also get created along the file. And of course, when an AV considers a file malicious, it will try to remove it. And if we can manipulate this process, maybe we can remove arbitrary files. So what? Well, many times privilege escalation. Because if we can remove arbitrary file, we can, for instance, remove files that we can later replace. For instance, in C program data or in C Windows temps, the default access rights on Windows are allow unprivileged user to create files and directories, but not to modify existing ones. So if we can delete files in this directory, we can replace them because we can create a file that do not exist yet. And of course, we can do it target AV with this, but this also works for instance, with other program like installers. On AV, we can trigger it, for instance, by putting the file manually into quarantine, as we saw with SCP. Or we can use some auxiliary tool like the file shredder or the cleaner feature if it also runs with high privileges. Or we can make the AV believe that the file is malicious. We'll see an example in a minute. And to bypass access checks, we can of course use uplocks if there is a TOC2, or we can also use other techniques like process injection or other path confusion bugs. To exploit it, we can, for instance, if there is a DLL that is loaded from a subdirectory of program data, we can, make it disappear and just replace it with an evil one, if there are the default, the inherited rights of program data that are also present of the AV and its content. We can then replace directly the DLL because of this default right. If we don't have the default rights, for instance, there are specific rights on the AV subdirectory, we can then just try to delete the whole directory tree, and recreate it with our own content. Of course, for that the bug needs to allow the recursive deletion of files and directories. And if we don't have any DLL loaded from these directories, but still have some other files that are accessed by the privileged program, we can then target these subsequent file operations, because if we delete the subdirectories and recreate them, because we own the file, we can now use the same technique as before, for instance in the file write or stuff like that, to attack the program. So if we want to delete an arbitrary file, what we can do is to try to redirect a file deletion. So For instance, we create a file that we know will get detected with the name of a file we want to remove. So here, license.rtf. Wait for it to be detected. And before deletion, but after detection, but before deletion, we replace again the directory by a junction. And then the file that gets deleted is actually our target file. So the proper way to do this is using, of course, uplocks. And when you can do it with uplocks, you should. But it's not always easy because sometimes there is, for instance, multiple kind of access and some that do not get locked, or for instance, multiple accesses, a variable number of accesses to the file before it's removed. So it's not always easy to place the lock correctly. So a quick and dirty way to do that is to create a directory, create a junction, drop acar in the directory, and then just keep exchanging the two, the directory and the junction, in a loop. And you have about 1/3 chance of a hit. So here is an example PowerShell snippet to do that. And it works surprisingly well in many cases. And because we can retry these as long as we want, even if we didn't succeed on the first try, well, we can just relaunch it and retry. Another interesting thing is that just before deleting the file, many AV will perform some operation on that file or in the same directory of the infected file. So, for instance, it will create a temporary copy of the file, or it will rename it or move it somewhere, or create a temporary copy. So we can actually exploit that part, these actions. So, for instance, we'll see how we can exploit it for arbitrary write. But for arbitrary read, what we can do, for instance, is to use the technique seen before to delete a file we want to get the content of. And just read that content from the quarantine file. So if the AV create, for instance, a temporary copy, or just put it in the quarantine file and the quarantine file are user readable, we can just read the content of the file that we just deleted from the quarantine file. Again, we'll have to unxor it or something like that, but we can get to the content. And for arbitrary file write, I'll take an example of a copy or rename operation. If, for instance, the file acar.exe that we just dropped will be renamed to acar.tmp, we can basically proceed as such. So create an uplock to log the process before that copy or rename operation. Again, change the directory to a junction to RPC control, and create two symlinks, one with the acar.exe that points to the file we want to copy, and the other that points to the file we want to replace. Because the AV process will try to copy acar.exe to acar.tmp or rename it. And of course, if it has the overwrite flag, well, you'll guess what happened. It will actually replace cmd.exe to sethc.exe. And if we don't have the overwrite flag, for instance, we can just make the acar.tmp point to some non-existing file name instead in system32, and then use the jackup trick again to load it. So, other demo, other AV. So here we create a temporary directory and drop acar in acar.txt in it. Not sure we will see it, but oh yeah, we see that the file got detected. And we set an oplock on removal.log, which is a log file that we know will get accessed because we observed it with a procmon, for instance, and we know it will get accessed before the actual operation that we want to target. So we use that to log the process, the thread, just before that operation. And then we see, is it running? Sorry. We see that the oplock just triggered. So before unlocking it, we can just create here. So we remove the temporary directory and replace it with a junction and combined with a symlink, object directory symlink, that is named acar.txt and that points to our payload. So here getSystemShell.exe. And we use a bait and switch tool to create another symlink, which this time is named acar.txt.ussdis, because that's the name that of the temporary file that acar.txt will get renamed to. And we make it point to uluhandler.exe, which is a file, an executable that is accessed, that is used by F-Secure Safe during updates. And we also added an oplock to that file, and then redirect it to another path, which is actually a file that does not exist. This is to prevent the actual deletion, because of course, after renaming it to a temporary directory, to a temporary file, sorry, F-Secure will try to remove the file. So before the removal, we just redirect the symlink to point to some other path that actually does not exist, so that the removal don't remove our payload. And we can now just go to the GUI and trigger an update, and here is again our system shell. You're very generous. So here are some of the bugs that were found during this research. We can see that there are a lot of AVs in there, but there are also the last 5 are actually other products. So of course AV are an obvious target for this type of bugs, but there are basically all products that are that have a privileged component, so privileged processes that do stuff with the file system. So that's quite a lot of products, can also have this type of bugs. To prevent this type of bug, what you need to do is, not break the security boundary in the first place. So use, for instance, impersonation or other restriction when you access files, especially files that are the unprivileged user can have some form of control over. You'll need to harden the product itself. So, for instance, to work on fully resolved path, make sure that your file is locked before the checked and until it has been used, and harden all secondary tools as well. And for defense in depth, you can also try to reduce access rights and not do dangerous stuff like loading code from program data subdirectories. Of course, all of these actions will create logs. Well, the attacker can try to maybe use the same bug to delete the log files or stuff like that. But if you have proper forwarding, you can correlate this log with other file system activity to try to detect this stuff. And because they use many operations that are not used by your typical Windows application, you can also create behavioral signatures. For instance, if you have a process that creates a lot of uplocks or exchange a directory and a junction a high number of times, maybe it's suspicious. One of the main takeaway is, of course, that you have to balance risk and benefits for when you're considering deploying an AV, and you have to consider the use case and the threat model, especially if your AV have easily exploitable bugs. So for vendors, of course, they need to reduce this attack surface and kill all the easy ones. And for defenders, I would encourage you to also test your vendor's security software and make sure that you have proper logging and forwarded, even for low risk events like just ACAR or stuff like that. And for pen tester, well, basically all privileged software is attack surface, including AV. So, well, happy hunting. And that's it.
Thank you for the timing and presentation. So we have time for questions, comments. Yes?
Did you try to automatize this process of like I'm the automating guy. So automatize this process of like creating the file, loading it into the antivirus. And I mean, my idea would be like by phishing, you just drop some code on a machine and then it would do all this process automatically and then like create some service that would contact you as an attacker later. Like do this kind of exploitations, not in local, but.
So no, I've not tried it. Yeah, that would be indeed an interesting idea to try.
But do you think it's easily feasible or?
Not sure it's easily feasible. I think you would have to spend a lot of time to adapt this kind of test to each AV engine. Yeah. So that would probably be the most time-consuming part.
Thank you very much.
Thanks.
Other question, comments? Maybe how do you discover this kind of flow? What was the intuition to try this kind of?
The first one was actually during a gig I did for a client. They had two endpoint security solutions, one AV and one other solution, and we had some misconfiguration that would allow us to get an easy system shell. But there was some AV that was one of the two AV that blocked the execution of a legit piece of code that was the piece that was vulnerable. So we used the second AV to delete the first AV so that we could execute this one. Because when we tried to remove the second AV was SCP. We tried just to manually put the first one into quarantine. We thought that it got refused, but that it got refused really quickly. But when we tried with a dummy file, it was a bit longer. So we suppose that there was some kind of talk-to bugs in there, and that's how we started looking at this.
Okay, thanks. More question? You want to eat? You don't want to wait 7 minutes? No more question? Okay. So, just an announcement. We resume at 2 o'clock. So you can have a great lunch in the place where we have a break at 10:30. So thank you very much. Thank you for the speakers and good lunch.